we now start section 1.3, which is about direction fields. If you recall from Calc 1, dy by dx, which could be any function in x, y, or just in x, or just in y. But what does this give us? So dy by dx, if you recall, is the derivative, of course, but what it is associated with is the slope of the tangent line of a curve to a curve at a certain point. So if I want to find the value of the dy by dx at a certain point, a, b, so what happens is that I get a number. So I plug the a, b in the function f of a, b, and it will give me a number. What is that number? That number is the slope of the tangent line to the function or to some curve at the point AB. So if AB, this FAB or dy by dx at AB comes out to be like 3, so it means the slope of the tangent line is 3. So how would you think about that? Well, it would be, if you imagine like a x-axis and the x-axis and the y-axis, or vertical and horizontal axis, then one slope will go like this. So a 3 slope may be like that, or maybe even like that. So that's what you have to do in this case. We have to imagine a small, short line segment, and in some cases, in some computer algebra system, they draw it by drawing a little arrow, but the line is enough small, very small line segment. So then we put these line segment, or we find these values of the dy by dx at few points, and then that gives us an idea of what the solution will look like. And it also can give some other information about the solution. So let us look at the example when we have dy by dx is equal to x squared minus y. Now if I want to find the value of the dy by dx, which means the slope of the tangent at the point 1, 2, I just plug this point in the function here and end up getting -1. So the slope of the tangent at the point 1, 2 to some curve is -1, and at 2, 3 the slope is 1. Now it's tedious to draw these by and even to calculate and then draw them by hand. So we are going to use a CAS, a computer algebra system, to create the direction field for us, and then we can roughly draw maybe some solutions and maybe get some other information about the solutions. So let's see in this example here. This is the direction field of the in example 1 part A. So the given equation is dy by dx is equal to x squared minus y. So below it, this is the direction field for the x squared minus y. So if you notice, we can see some shapes. So over here, there is these looks like straight lines, but like something going a little bit like that, and over here also a little bit like that. But over here in the middle, you see there is like you can literally see things moving like this. Okay. And on this side also moving like that. So but if I start from bottom, so something coming like this. So something coming like this and going like that. Okay. So now look at the right side. So the graph on the right side here. So these are some solution curves drawn using this direction field. So if you want to look at a particular solution at like a solution curve passing through a certain point, we can always get an idea of it. For example, this we can call the solution curve passing through 0, 2, and this one, for example, what will you say from between passing through 0, -1? So somewhere here we will have -1, maybe here, So you see the curve goes like that, and so on. So this is the curve at 0, 0. This one, and so on. Okay. So all the curves, it looks like are kind of getting together over here, or they are going to infinity, but through this path. So, and also we can see easily where the functions are increasing, where they are decreasing, roughly where they will have which function will have local min, max, or just a local min, or maybe just a local max, if there are any such ones. And so this is what the direction field tells us, and that is how we look at it. And or sometimes we will see that as x goes to infinity, so we can find the limit of the function. Well, let me say not this function, limit of the actual function, so limit of y of x as x goes to infinity. So what is that? In this case, it will be infinity, because these are all going to go to infinity. But let us now look at a couple of more direction fields. So on the left here, we have the direction field for dy by dx is equal to minus 2y. So for that, the direction field here. So if you notice, a curve passing through, for example, 0, 1. So it looks like something coming from the top and then becoming like this. Now this is showing, if you notice this line here, it's showing that it is going like this, but it is not going to cross the x-axis and go to the other side. It looks like x-axis is becoming a horizontal asymptote. So if you look at something over here, going like this and becoming like that, okay? And from the bottom, they are coming and going like that. So if you notice now, as x goes to infinity, the functions are going towards 0. So 0 can be called the limiting value of the function of our curves. In part D over here, you see the direction field for dy by dx is equal to negative y over x, and over here we see curves like this. On this portion in the left or the second quadrant, like that, and in the third quadrant something going like this, and the fourth quadrant something going like that, where you see the values are becoming like the x-axis and the y-axis are looking like asymptotes to these functions. I forgot to discuss one thing in part C, which I will do right now. So notice here we don't have any x, so x in here. So what happens as x goes to infinity? Well, we can tell from our direction field that the function is going towards infinity. So what happens when y is 0? When y is 0, you can see from here the result that we will get will be this line, because when y is 0, if you notice, the curves are going almost flat. So we get the axis as our y is equal to 0. Now if we look here in part D, when x is 0, you can see that 0 is coming in the denominator, so the function is not defined. So we are not going to get the 0 if y is different from x, which is 0, but y is not 0, then we will never reach 0, and it will be the asymptote. The x-axis will be the asymptote. But if y is 0, then and x can be anything, then we will get the horizontal line, because y is 0 will make this, if x is not 0 but y is 0, it will make this quantity 0. But what happens at 0, 0? Well, there will be nothing, so we might be skipping the 0 and that will be our solution. Now let us look at the actual solutions of these equations, because it's easy to find the solution. So we have dy by dx equals to minus 2y. Now I will do something here which we are actually going to learn in chapter 3, and this is called separation of variables. Okay, and this is called an equation or a differential equation in which we can do this technique or apply this technique is called a separable differential equation. Separable, that it can be separated. So we can first do this, think of these as differentials. So I move the dx to the other side, so I get this. Okay. Now remember, differentials arise while integrating functions. So for example, you can be integrating x dx. So we put dx with that. If you have x dy, it means we are doing, this will be treated as a function of two variables, and you know how to do that. The answer will be x times y plus a constant plus a function of x. But here we are not doing, because we do have a dy or a dx in our equation, and we have both of them. So any expression, anything which has a y in it should go towards the dy side, and anything which has x in it should go to the dx side. So there was a negative sign here. So you see we have a y here which we can easily make it go to the left side. Well, we can take the negative 2 along with it, but we don't need to, because negative 2 could stay on the x side or on the y side. It shouldn't make a difference. So just let the y and negative 2 stay here, and we divide by y. So when I divide by y both sides, I end up getting dy over y is equal to minus 2 dx. So we can think of this as integral. Now I integrate both sides, so I can put the integral sign right here. But now we can think of it as 1 over y dy equals negative 2 integral dx. So integrating the left hand side, we end up getting a ln of y and equal to the minus 2x, and then plus a constant. Now in the past, when we were doing, in Calc 3, when you learn functions of several variables, more than one variable. So if you are integrating a quantity like x dy, so when you integrate, you end up getting x times y plus g of x. Why g of x? Because we don't know whether the constant term, which is constant with respect to y, it could have an x in it. But here, because we are differentiating both quantities, the y and the x, so we will just get a simple number as a constant of integration. So we can just put a c here. Now often when we have a ln in our integration, a log in our integration, it is easier or it is convenient to put an ln in front of the c as well. This makes the calculations a little bit easier or more understandable. So I'm going to put it ln of c. Here I'm thinking of c to be a positive number, because otherwise I have to put bars. So in general, it should be ln of c absolute. Okay, so now we can move the ln of c with ln of y on the side of ln of y. And why do I do that? Because I can then apply one of the logarithmic properties or law and combine these two. So on the right hand side, I'm left with negative 2x. Now ln of y minus ln of c can be written as ln of y over c absolute. and this is equal to negative 2x, because I just rewrote the left side in another form. I did not perform any action on it. Next we do is, because remember our goal is to get y by itself. So next thing we do is we get rid of this ln. And how can we do that? We take we convert it to the exponential form. Or I have seen some people say that we put an e here and an e here, means we are raising these quantities, both things, to the e to the power of these, which is okay. So but basically you can see this by using the converting it into exponential form. So if you think of it like this, e raised to the power first quantity, so this side, as think of it as e raised to this quantity, and on the right hand side e raised to this quantity. So when you have e raised to ln of something, that becomes just that something. So I have now here y over c, and on the right hand side it is e to the negative 2x. Now note here that this side is always positive. So I can remove the bars from the left hand side, because this is always going to be a positive. So I have y over c is equal to e to the negative 2x, which gives me that y is equal to c times e to the negative 2x. So this is what I get as a solution. And if now, just to check it with our curves, the graph of e to the negative 2x will look like, so it will pass through 1, so just e to the negative 2x. It will be a function going like this. So where x-axis is the horizontal asymptote, and the function is coming on the left from infinity, and then it passes through 1. But what will be c times e to the negative 2x? Well, if it is c, then you can see when x is 0, the y will be equal to c, whatever c is. And so if I have the function, it will be like, let's say this is our c, 2, 3, 1, whatever, minus 1, minus 2, whatever. So, but c is positive. Remember, we took it to be positive, so we cannot go below. We have to stay above the x-axis. So it will be function like that. Okay. And if you go back now, we see this kind of behavior here with these solutions. And notice here that the limit as x goes to infinity of our function, in this case we notice is 0. So limit as x goes to infinity of our solution y will be y of x, or will be equal to 0. So here, if you find the limit of this quantity, that is also giving you 0. It makes sense, and then you can see, compare now if c is negative, you can already see that if c is negative, we will get a curve which is a flip of this curve, or this curve about the y-axis. So it will be a curve like that, which is what we are seeing in our graphs. Now, why did I went into detail about this one? Because this type of equations you might have seen before, depicts the decay curve. This is what we call the decay curve, or the model for decay of anything. The most common is the decay of a radioactive substance. So if initially it can start with a mass A, big A, and over time, what is the rate of decay of the particle or mass, radioactive mass, we can say that if the rate is negative k times a. So negative k times a means that the rate is proportional to the amount left. So k is different for different materials, for different radioactive materials. K will be different because of the substance, but the equation will be same, that the rate of decay will be proportional to the amount of the material at any time t. So that's what is represented in this equation. This is called the decay rate or radioactive decay, or just decay model. Okay. Now let us look at the second equation, second differential equation on the right, which is equal to negative y over x, dy by dx negative y over x. This is also something which we can solve by separation of variables. So notice here that we have dy is equal to negative y over x dx. So x and dx will stay on the left hand side. We have to get y to the x and dx stay on the right hand side. We should get the y to the left hand side. So we get dy over y equal to negative 1 over x times d, or dx over d. Now we integrate. So the left hand side gives me ln of y is equal to negative ln of x. And then if you want to add a constant, plus ln of c. So now I will move this one over there. I can move the other one as well, but I don't need to. I'll get the same answer with whatever I do. But here ln of y plus ln of x is equal to ln of c. Again, we will use some properties of logarithm, which if you are shaky about it, please review them. So this left hand side gives me ln of x times y absolute, which is equal to ln of c. Okay, let's put an absolute here. So now the ln go away. This is again a property of logarithms. So I end up getting x times y is equal to c. Now we can get rid of the bars, assuming that always we are going to get the negative can be combined in the c from both sides. Just to make it a little bit more easy to understand, it is something like y is equal to c over x. So this will be the solution. Now if you try to graph this function, for example, the simplest one will be y is equal to 1 over x, which if you recall is a piece here and a piece here, something like a hyperbola. And then if we have different values of c, you can see how it will change. And what if c is if we have a negative sign in front, then we will get a piece in these two quadrants. So for example, if y is equal to negative 5 over x, so then we will have a situation like this. So that these are the functions, or these are the curves you can see in the direction field over here. Okay, let me stop here and we will do more examples in the next video.